Hello, everybody. Welcome. We are talking today about capacitance applications, and we're going to talk about capacitance as a concept. So, want to just get straight to it here. So, in DC, we've got capacitors, and in AC, we also have capacitors, but it's important to note that you can have ones that are more suitable than those to the other. Capacitor is a two terminal electrical component that stores potential energy in an electric field. The effect of a capacitor is known as capacitance, and you'll see there at the bottom some of the symbology involved in this. You can have a fixed capacitor, you can have a polarized capacitor, or you can have a variable capacitor. And a polarized one is one that has distinctly positive and negative sides to it. So that one is very much really only applicable to DC circuits, whereas other fixed capacitors that don't have that polarization can have current flow through them both directions. And so those capacitors can be used for AC as well. So capacitors are really just there to store energy for quick release. Now, it can't store a lot of energy. It really is just storing voltage. It's storing the push in a electrical circuit. Um, it's important to note that it blocks DC current because it isn't actually like the two leads of a capacitor are not actually connected to one another. So it'll block DC. However, it will allow AC signals to pass through it, but it's not actually letting individual electrons go from one side to the other. And we'll get into how that happens in a little bit here. Because physically, what a capacitor is two plates separated by a dielectric insulator. Now, insulator, we know that word. Insulator just means that electricity doesn't want to pass through it. So if we've got two plates that are separated by a dielectric insulator, that dielectric part of it means that it's capable of allowing the push of electron through it, but not the electron itself. So that means that we can use the electrons on one plate to force electrons off of the other plate because electrons repel electrons. So let's take a look at this. Here is an example, just a quick diagram of a capacitor with no charge. Basically, the charge is equalized on both plates that are separated in the middle. Notice that our symbol here clearly shows that there is an open circuit there. There's this air gap or whatever dielectric material is in between there that prevents the actual electrons from flowing across there. What happens when we connect a battery to it is that our electrons flow and then they push the electrons off the other side of the plate. And it will continue to flow until one side is charged. Once we have all positive on one side, all negative on the other, then all current stops in a DC circuit. So what we've got here is a circuit that is just working for a moment until that capacitor is charged, and then it stops all flow through it. So it's basically blocking DC at that point. Once that capacitor is charged, it has the same voltage as the power source. 1.5 volts on the battery, that means 1.5 volts on the capacitor. If with the same capacitor, you could a lot of these capacitors they're good for up to 600 volts, but it just depends on what you charge it to. Now, for a small capacitor, the capacity is small, but large capacitors can hold quite a bit of charge, and that is voltage really, because they charge quickly and then they release quickly. So they're not good for keeping up with a constant current. It's really just to help maintain a constant voltage. So this state will continue until the two plates are connected to one another. So they will stay charged, and they'll stay charged for a long time. In fact, one of the things that you have to be aware of when you're dealing with capacitors is that they are kind of dangerous. In fact, your defibrillator has a little round portion of it off to one side. That's not the battery, that's a capacitor. And when it says charging and then does a discharge, that's from a capacitor. So, and it will stay charged for a very long time, and then it will discharge very quickly. So don't grab any capacitor, but particularly a large one, um, with both hands, because you'll shock yourself. It's always a good idea to discharge them in a safe manner by either touching the two leads together to discharge them, using a metal bar that you're insulated from, like using perhaps a screwdriver to touch those and make sure that it's discharged before you work with that capacitor. So there's an illustration in the book on page 104 that you can take a look at that explains the water analogy for a capacitor. It's a good idea to kind of get the water analogy behind capacitance, as well as inductance and other theories and concepts within DC circuits. But capacitors are used in both AC and DC circuits for different things. So it's an important thing to kind of get what it's doing. Here is a bit of an illustrated example here. We've got a battery that's charging this capacitor, and we have a light bulb on one side. What happens when we're charging it? What happens once it's fully charged? What happens when we remove the battery? What happens when we bridge the gap between the two battery wires? What will happen? So I'll walk you through this. So just like what we saw in the earlier simple diagram with the pluses and minuses, during the charging phase, there will appear to be current flow because the electrons are flowing through the light bulb to the negative side of the capacitor, and they're pushing electrons off of the other plate of the capacitor and going around down below. This means that the light will come on while it's charging, but once it reaches full charge, all current will stop and the light will go up. Then that's the steady state. That will be what happens once it's fully charged. It will be up. The light bulb will be out. There will be no current that's flowing. If we remove the battery, we haven't improved anything for current to flow by removing the battery. But, so like light stays out, but if we bridge the wires between where the battery stood, then current will flow in the opposite direction. And so the light will come back on and fade out until the capacitor is fully discharged. The following slide here just contains the words for explaining what I just explained, so you can kind of look at that in your own time. Capacitance is defined as a charge over voltage. So C for capacitance is Q divided by V. Q is our symbol for charge, and V is voltage. So the unit for capacitance is the farad, which is 1 coulomb per volt. So farad equals 1 coulomb per volt. Now, that is F-A-R-A-D. I didn't misspell that there. I had a student make a mistake once and called them ferrets, like the little Weasley animals. Do not. Just do not. It is farad. And farad is a really quite high, it's quite a large unit, because coulombs, as we discussed before, are a large unit. So when we're talking about a farad, we're more likely in capacitance to deal with things that are microfarads or millifarads or Millifarads, microfarads are much more common. Picofarads are even commoner. So you will see it in that range. So keep that in mind as you're dealing with other equations, that you're going to deal with those same unit conversions between them. When you're dealing with capacitors in series behave exactly like resistors in parallel. So it's 1 over C total equals 1 over C1 plus 1 over C2, etc., etc. And that means that when two or more capacitors are connected in series, the total capacitance is less than the smallest capacitor in the group. And this makes sense because the amount of electrons that it has to fill the next one over and the next one over is limited by how many are on that one. So the smallest one is always going to be less than the smallest one because it's kind of just passing it along, passing it along, passing it along. So why would we hook them up in series? Well, the benefit of in series is that capacitors can withstand higher voltage at the cost of decrease in total capacitance, because obviously we're reducing the capacitance by putting them in series. So it can withstand a higher voltage than any individual one, because it's sort of splitting that voltage up a little bit as far as within the component. Capacitors are far more often used in parallel in DC circuits. They're used in parallel to buffer current, so you will see them used often in there. And when they're used in parallel, they act like resistors in series. In other words, it's a simple addition. The C total equals C1 plus C2 plus C3, etc. The benefit there is that you've got more energy stored the more capacitors you add in parallel with one another. There are essentially two types, polarized and non-polarized capacitors. And when we break that down even further, you can look at what capacitor types there are. And, basically what it is it's describing that the electrolytic, or the dielectric insulator that's in between. So you've got air core. Just means that it's air in between there. You've got vacuum, you've got aluminum electrolytic, you've got tantalum electrolytic, polyester film, polypropylene film, silver mica, ceramic, and you'll recognize that a lot of those are insulators. So the electrolytic ones are the ones that are generally in the polarized category. And that's because the electrolytic reaction that's happening inside of there on charge and discharge is happening between two aluminum plates or tantalum plates. And that can only work in one direction. It won't work in the other direction. Now, let's talk a little bit about capacitors, what they're used for. Like, why did we learn all this? So, one of the biggest things is it's used to maintain a constant voltage. If we place a capacitor in parallel with something in, say, in a power supply, what that's going to do is that's going to level out any fluctuations that are happening in that DC power supply. It will filter out any fluctuations in that, because it will charge when the voltage goes high, and it will discharge when the voltage goes low. And so for that reason, when we place these in parallel in DC circuits, we're really just trying to maintain a more constant voltage. In AC, it's used to filter DC out. Now, wait a minute, how does AC get through there? Well, AC gets through there because it pushes it, and then the current, it pushes the electrons off of one plate, and then the current changes directions, and then the electrons swing back and push it off the other one. So it's just kind of a little barrier. And what the effect of that is, and we'll get into this in another video on reactance, is that it actually shifts the phase angle of an AC current, of alternating current. So it shifts that phase angle And it provides a resistance essentially to an AC circuit called reactance as a result of that kind of forcing it through that item. And we'll talk about that. That's a subject for another video on reactance. So we'll get into that there. It's also used to start motors. So when we get into talking about motors themselves and how they work, three-phase induction motors are pretty easy. They don't really need a whole lot of help getting started. However, if we're doing single phase, it's going to get a little hard to get it started rotating. Once it's rotating, it works pretty well. But getting it started, we need a second set of fields, and we need to energize those fields. And so we do that with a capacitor that is essentially energizing those fields in sequence and until the motor is started running. So you'll see capacitors, the little hump on the side of a single phase motor contains a fairly substantial capacitor. That's what's in there to start that motor. You'll also see it being like smaller capacitors being used for timing functions that take advantage of the time of charging and the time of discharging and thresholds of those, as well as other electronic functions. Those applications are going to be discussed way more in depth in another class called embedded systems. So we're not going to really deal with those functionalities here in this class, but that is another application for it. That's kind of the basic lowdown on capacitors. Now, on your systems, when we're working in class, you're going to deal with capacitors in multiple ways. There are capacitors that are inside many of the components that are in your enclosure. They're used to maintain constant voltage. So in the power supply, they're used to maintain a constant voltage, even though the alternating current that's coming in there is going up and down and up and down. They're used on within the variable frequency drive that's going to drive our motor for our conveyor. There's even capacitors that will start AC motors if we use a different style of conveyor. We have some that use single-phase AC motors as opposed to three-phase motors. Those are going to be the motors that have that capacitor to it, and you may be wiring one up for those if you're using that style of conveyor. So that's kind of where you're going to see capacitors in this class, and we're going to go through, and when we get to the other video later on reactance, you will see how that affects AC in a much more comprehensive way. But other than that, that's just kind of like the starting point of where capacitors are. We want to get this out of the way. We want to get in, and we want to get some of the basic DC concepts out of the way, and then we'll go more into depth on how these things are applied a little later. So there you go, introduction to capacitors. We'll see you in the next video.